So in this part, I'm going to continue the topic, and I'm going to discuss some advanced topics in this area. And when we say advanced topic, I think something that we cannot miss must be some big models, and also the currently very popular concept about few-shot learning. And I'm also going to briefly talk about model evaluation at the end of the talk. So let's first have a very high-level recap of what has been covered so far. In the first talk, we have been talking about the general landscape of image text pre-training. And here we have been talking about two kinds of VLP methods. One traditional early method is based on object detection to have the feature, to get the feature offline. Some example, as we discussed, include the Lexmert, VLBERT, Uniter, VLBERT, and etc. And then we come to the current prevailing end-to-end pre-training methods, and we discuss what we can use convolutional network or using vision transformer so that the whole model can be trained from end to end. Pixelbert, Sohu, YLT, LBIF, meter, blip, and etc. Just now we have been talking about unified image text modeling in terms of both output format, how we can unify text token generation and bounding box generation, such as VLT5, MDiter, Unicorn, OFA. We have been also talking about how we can unify the architecture. Can we just use a unified transformer to perform this task, such as UFO, WIMO, and the recent VL submit paper? Note that a typical setting or a typical academic setting for all these methods, they are so a typical setting for them is like this. In terms of the model size, they typically either base model size or large model size. And the number of parameters in this kind of model will include 110 million or more than 300 million parameters. And usually, in order to have a fair comparison, a widely accepted setting is we are going to pre-train such a model on 4 million images in total. And this will consist of images from coca, visual genome, SPO captions, and the conceptual captions, 3 million. So this is good. So what are we going to offer in this talk then? First, in the first part, I'm going to talk about big multimodal foundation models beyond base and the large model size, and also beyond the 4 million images setting. Examples include simvrm, coca, and the Git model. But I'm going to talk a little bit more detail about the Git model and what's the capabilities that has been shown by simply doing large scale pre-training. In the second part, I'm going to talk about multimodal few-shot learning, right? How can we enable in-context few-shot learning by just providing a few in-context examples to your model? And examples include Frozen, Pica, and Flamingo. We will go into the details of them. In the third part, I'm also going to talk about model evaluation. Besides all the current standard benchmarks that we use, such as VQA and the image captioning, then what's the next, right? As you know, all the numbers are pretty high, and we are kind of cannot improve further, right? How can we really or benchmark this kind of foundation models? And we will briefly cover diagnostic tests, challenge sets, and also probing analysis. Okay, so without further delay, I'm going to first go into the first part, which is big model. So when we before we talk about multi-model foundation model, let's first say what are big foundation language models. There is a workshop last year, summer, right? I forgot it. Yeah, so it's in August. So it's called a workshop on foundation model hosted by Stanford. And in this workshop, people are discussing and defining what is foundation model. And hopefully a foundation model is, we hope to train such a model that can be pre-trained, can be large scale pre-trained, or if you can do small scale pre-trained, it's also okay, right? As long as you can transfer your pre-trained model to a very diverse set of downstream tasks, right? Some very well-known big language foundation models, such as BERT, right? I guess everyone just know it. We have BERT base and also BERT large. We also have a GPT-3, right? And even the recent the PALM paper. So in the GPT-3 paper, we have more than 175 billion parameters. You can really just think, these guys are crazy, right? They are training such a big model. And in the Palm paper, the number of parameters are even larger. It's more than 540 billion parameters. But then how about big multimodal models? So here with foundation models. So here models, we define models that have either billion level parameters or use billion level pre-training data are considered big in this context. But before I dig into the current big foundation models, I need to first note that foundation models are not necessarily needed to be big, right? Ideally, if we can train a base size model, and ideally this base size model can have very good performance and even can perform, for example, in context learning, right? This is even better. So foundation models are not necessarily to be big. It's just happen to be nowadays all these foundation models. If you want them to have strong performance, it happen to be big, and it's kind of have some scaling law so behavior so behind it. And also here we will not talk about clip like dual encoder and also text to image big models such as DLE and Imagen. So in this talk we are more focused on fusion encoder. That is we want to pre-train a model to perform the standard salvation language tasks such as QA and captioning. And for dual encoder and text to image, this will be covered in more detail in the afternoon session. So in order let's to say the progress, we need to have a figure, and this is the figure. So let's take VQA as a good example. As you can say from the beginning, so we can roughly divide the progress of VLP into 3 stages. The first stage is the red curve, which is task-specific methods before pre-training. And the blue curve are all the methods using the OD-based methods. And then the red curve is the current prevailing end-to-end methods. So over the years, the number of VQA has been improved from roughly 65 to more than 82 nowadays. So something must happen inside, right? It's non-trivial to improve your model by such a huge margin. And we can say in the first stage, task-specific methods, roughly VQA number can go from 65 goes to 70 something. And then by using OD feature, the model can go from 70 something to 76. And as end-to-end methods become popular, as you can see, indeed, in the very beginning, end-to-end methods are not that strong, but you can see it catches up very quickly and it's current sorta. And in order to achieve this sorta, there are 2 driving forces. One is large model sizes. Another is large pre-training data. They have been the driving force for sorta performance, and especially for captioning tasks. The number of pre-training data you will need to have a good performance is very important. Surely we are not just sorta driven, right? So in the later slides, I will also briefly talk about what's beyond the sorta tracing in later slides. So this slide, it's a high-level summary of the current big multimodal models that we consider as so big. There are 2 blocks, and also there are all the references below this table, so you can have a track into all these models. So as you can see in the top part of this table, they are dual encoder, so which we will not cover. But basically, they are all using the so-called ITC loss, as we introduced in the first talk, is image text contrastive loss. And in the second half of this table, which is the model that we're going to cover. And also here we try to calculate how large the model is. And this is rough, some of the number are just roughly estimated because we just cannot have exactly the number of parameters this model has. But roughly you can see the model sizes have been, at least for the current model, it's just so roughly like 1 billion model size. And so if we take a closer look at this table, for example, for the image encoder, one exception is the Lemon paper. So the Lemon paper, they are not using a vision transformer or ResNet. They are using an object detector. So the size is relatively small. And then sometimes it's not easy to distinguish or differentiate what is the image encoder, what is the text encoder, and what is the fusion model when you read the paper, right? Because sometimes the fusion part are also considered as the one part of the image encoder in some in some papers. And the fusion model is also called some text decoder in some papers. But then if you just look at the total number of parameters, you can still roughly can roughly have a sense of the trend. In terms of the total number of parameters, one model that I want to point out here is about the Flamingo paper. This is probably the biggest multimodal foundation model to date. And one reason is due to they have a big language model inside. So due to the language model is very big, so the overall model size is also very big. And the use of why this such a big language model is needed will be covered in later slides. So in the pre-training data column, as you can see, it's also roughly 1 billion so pre-training data. So in terms of either it's image text format or it is image label or image tag format. So one exception is the meter model, because here we only have using 20 million image text data for pre-training. But here, actually, the image encoder inside the meter model, they are pre-trained using 900 million image text pairs. So if you look at it from end to end, it's still big. In terms of the pre-training task, basically you can have one observation is language modeling. Either it's a prefix language modeling, or it's the standard language modeling, or it's masked language modeling, or it's the combination of language modeling plus the ITC loss, such as used in the Wemo++ model and also used in the coca model. You must be curious about what's the model looking like, right? So this is how this model looks like in a high level way. Clip, Align, and the Florence model, they are dual encoder that only use ITC loss for pre-training. And the Lemon, Git, and the Flamingo model, they are in the second category. So they are fusion encoded. And Lemon uses a strong OD, which is short for object detection module, to first extract the image features offline. And then the Git model uses a big swing-like image encoder, but with a small text decoder, which is interesting. And on the other hand, the Flamingo uses a relatively small image encoder, but plus a big text decoder. So I think this is all due to the model design purposes are different, which we will cover in later slides. Since only in MLM and LM loss are used for pre-training in Lemon, Git, or Flamingo, so it is not friendly to fast retrieval. Because if you want to do fast retrieval, we want to kind of use the clip-like model, right, using the ITC loss. So this is the third part is the LBIF meter coca model. They are looking like this, and they are using an encoder only design. But actually, it depends on how we call it, because in some paper, the fusion model can also be used or just called as the text decoder as well. And here we consider it as a fusion model because they take the information from two modalities as the input. In the meter, the ITC loss is not used, while in LBIF and in coca, ITC loss is used, which enables fast retrieval. There are also models like Blip and the Fiber that performs fusion in the backbone. And the model, the paper reference are shown in the bottom of the slides. So in the middle, there's a simvrm, right? So simvrm uses an encoder-decoder design and is pre-trained with the prefix LM only, LM loss only. So let's have a closer look at what is the simvrm. So the simvrm, as a high level shown, it's an encoder-decoder design. The model was pre-trained with prefix LM on 1.8 billion image text files, but unfortunately, the data is private. Then what is prefix LM? So prefix LM is it's a popular pre-training task in the NLP community. So the basic idea is you are going to partition the text input randomly into two parts. And then the first part of the text input will be sent into the transformer encoder, while the later half will be sent into the transformer decoder. So naturally, additional text corpus can be naturally used for pre-training, right? Because you can just simply ignore the image input, then it's done. And so since the high-level message in this paper is, as long as you have big model and enough data, simple pre-training loss is enough. So here, after they only pre-train with the prefix LM, they have very strong performance after fine-tuning. And here we show the performance of VQA. Before the simvrm paper comes out, it is really hard to believe the VQA performance can be up to 80%, right? Usually we play with 74, 75, 76 at the best, right? But then simvrm tells us it can be suddenly boosted to 80%, which is really a surprise last summer. Besides SOTA, after fine-tuning, it also shows strong zero-shot generalization capabilities. And here the table shows the zero-shot image captioning performance. Well, they show using a prefix prompt like a picture of generally will improve the quality of decoded captions by a lot. They also show few shot performance, but then in their context, the few shot is more like using more than 1% of training data. So it's not a real few shot setup. It's more like a semi-supervised or low resource setting. Due to the use of a generative approach, so it can enable open-ended VQA. Usually VQA is considered as a classification problem. But then naturally, we actually hope, right? The VQA is open-ended by nature. When people ask you a question about an image, ideally you hope your model can answer the question in a free-form format, rather than choosing from a fixed vocabulary. They also show strong results on ImageNet linear probe because they try to pre-train the image encoder also from scratch. So inspired by the simvrm paper, there's another paper called Lemon. And the author in this paper, they try to study the scaling law of VLP model for image captioning. So in order to do this, what they do is the following. They want to scale up the model size. So the model size range from 30 million parameters to 675 million parameters. And also they want to scale up the data size. So they have pre-training data from 3 million to 200 million parameters. And here is the scaling law. And we can say there are two sub-figures. On the left, it is the image captioning results on coca. And the x-axis is the pre-training data size. And the y-axis is the SIDA score on coca. And also on the right, it's model results on the node caps, which is divided in domain, near domain, and out domain. So the first observation is strong performance boost can be observed, especially for out-of-domain captioning with large-scale pre-training. Due to during the pre-training phase, the model can see a lot of different visual concepts. So this will help you boost the performance. If you see the margin highlighted in the red, so dashed boxes. Another observation is the larger models usually benefit more from the large-scale data. So if your model is not big, so for example, if you see the figure on the left, right? If your model is not big enough, even if I send you many data, your performance will be saturated relatively easily compared with you. So if you have a big model, due to you can have more capacity. They also collect the so-called out 200 million data set. So there's no human annotation required. So there are several properties in this data set. One is it covers rich visual concepts. As you can see from the table, right, the number of unique the unique gram. So in this data, so if you have a large data set, usually the unique unigram will be will be very big. Also, during the pre-training, the data is not even well-formed sentences. If you consider the captions in this data set in the first row, many of the captions, they are just the labels. For example, from Bay Horse, or on the most right image is Mahjong, right? Mahjong board game, if you know it. I guess many of you know it. So another is some do not exactly reflect the image content. If you see the top, the bottom left two images, the first image is a woman given a gesture, right? And then the caption is, I got you. So it's not reflecting what the image is about. And it's more about learning the common sense or learning the social common sense, right? And then the second image is a Happy Father's Day, which I think echoes today's topic quite well. So Happy Father's Day to all the fathers in this room, if you are a father. So this is how Lemon look like. And by simply doing this, they have SOTA performance on public benchmark. And also they show the model can do zero-shot image captioning. There are in each picture in this slide, there are 3 captions, which is B, F, and Z. And we need to care about care more about the B and the Z. B is no pre-training, and the Z is pre-training only, which shows the zero-shot captioning performance. And actually, you can see Lemon is capable of recognizing diverse visual concepts pretty easily, right? As you can see, all the concepts in the bottom line is very smart. So for example, a picture of a dinosaur skeleton, a picture of a killer whale, and a picture. So the model also knows. So the first image is about a tuba. And inspired by Lemon, further follow-up work include Git. So the same story as Lemon. Git is also a simple generative image to text transformer, but the difference is it's trained on larger scale data, which include 800 million, while simple language modeling loss. And also, instead of using an OD module, the authors here use a big swing-like model as the image encoder, so that your model can be trained from end to end. The image encoder also needs to first pre-train while image text contrastive loss. And the same strategy is also used in Flamingo. For example, the Flamingo has a frozen image encoder, right? And this frozen image encoder is pre-trained by clip-like loss. And in coca, the clip loss and the caption loss, they are used together. So in a high level, it is the same, just an image encoder plus a text decoder, or called a fusion module. So since the model is about captioning, so the model can be used for captioning very easily. And then when it adopted to VQA, it's just consider VQA as a text generation task while using the question as the prefix. The video task can also be easily handled while concatenating the image frame, the features. So it have a very strong performance and also has the first human parity on text caps without even using OCR. Basically, it tells you the model is not explicitly trained with syntax recognition capability, but the model indeed shows very strong syntax recognition capability. And this is some challenging case in the text caps data set, right? Basically, you need a model to know what all the important syntax in this model. Later, in next slide, I will show some visual example. And also Git provides, So Git provides a generative scheme for image classification and the syntax recognition. So basically, this means when we do image classification, we are going to just generate your class names token by token, instead of treating it as a one-hot vector. And then actually the performance is very strong. Git also shows it can do syntax recognition automatically, basically. So in the last block, there are two rows. In the first row, it's a Git model fine-tuned on text cap, and you can see on standard syntax recognition benchmark, the performance are very strong. And if you further fine-tune on task-specific data, the performance can be either so improved. But the good thing is, even without fine-tune on the task-specific data, Git shows very strong performance on average, close to SOTA. So here is some capabilities demonstrated by Git. And all these capabilities demonstrated by Git reflected by the captions generated by Git. So, so as you can see, the model can automatically detect the syntax, long text, curved text, blurry text, occluded text, and also it can recognize the contents inside the table and the chart. The model can also know food, such as mapo tofu, right? And also money bill logo. And the model, no, this is not just a plan, but it's a data plan. Yeah. And also landmark, character, celebrity. So the model not only know this is a woman, but more importantly, the model know this is Marilyn Monroe, so automatically. The model can also do product tag and photo. So this is about generative pre-training. But how about we combine them together? And this is the basic idea on the coca. So on the coca, it's all the model that are trained from scratch, including image and the text encoder, and is pre-trained by a combination of contrastive loss and generative loss. And also, you need to pre-train on large data. However, the data is private in order for you to have good performance. So here is some high-level performance shown by the coca model. You must be curious about, oh, all this data, they are private, right? How can we do it? So let's let's have a quick summarization. What are the publicly available pre-training data that we can have without, so if you are not in Google, right? Or if you are not in some other company that you do not have this data. So in the Flamingo paper, they have a summary of the current, publicly available pre-training data that we may be able to use. First thing is coca 12 million. So it's a larger version of, CC 12 million. So it's a larger version of the CC 3 million. We also have the local narratives. So the image can correspond into a very long caption. We also have the weight data. So the weight, so the WIT data, so it features images and multilingual text collected from the Wikipedia content pages. We also have the ref caps collected from the subreddits, right? So it's a data set, the so-called created by the people and for the people, because it contains everyday things that users like to share on social media. And we also have Leon 400 million and 5 billion data set, right? They released the data set. However, it indeed remains unclear how useful each data set is, but at least it provides us the opportunity to use different data set for pre-training. So with big models being introduced, I'm going to talk about in context, so few-shot learning. Well, if you are the first time to hear about in-context few-shot learning, then this is a very high level, so introduction. Getting SOTA performance while full fine-tuning, which is great, right? But then the question here is, can we train a model that can quickly adapt to different downstream tasks while only providing a few in-context examples? And this is a figure in the GPT-3 paper, right? On the right is the standard full fine-tuning setting, and on the red boxes highlighted in this slide is the few-shot setting. Basically, you are going to provide some instruction and a few examples. Here is taking the machine translation as the example. And after you've given the model a few examples, the model can know, oh, now I need to do machine translation, so let's do it. And in the GPT-3 paper, they show the model can have very strong few-shot learning capability. So how can we do few-shot learning in the context of multimodality, right? The first idea is frozen LM. Since language model has shown this capability, then let's keep it frozen, right? So we need to have a strong language model that is keep frozen, and then we try to align an image encoder towards this language embedding space. And this is the figure in the frozen paper. So basically, you have a language model, but now the prefix is not text, but rather it's so image encoder, and then you will do the gradient back propagation to learn this visual encoder. So if you are familiar with the literature, and another method is quite interesting is doing the opposite design is the lead paper. So in the lead paper, they focus on zero-shot transfer on image classification, right? So they are still using the clip model, but in their case, they frozen a strong image encoder. And in the frozen paper, since they care about in-context learning, so they frozen the language model. So instead, but then by doing this, interesting in-context few-shot learning capability can be inherited from the frozen LM. And still, the image encoder they use is normalizing free ResNet. However, an image is compressed into 2 global vectors rather than using a set of grid features, which can be a lot, right? So here in the frozen paper, they mainly want to provide the two vector, so which can be global, but as you can see, this may also sacrifice performance due to you only compress an image into 2 vectors. So in later methods, they have shown using a lot of vectors is also doable, but then you need more computing resources. And the language model is a 7 billion parameter transformer pre-trained on C4. After doing this, they show some curated example here. For example, in the first row, all the pictures and the captions on the left, they are in context example. This is a person like happy, this is a person like sad, and this is a person like what? Like a surprise, right? They can generate such an emoji. And they also have the second example and the third example, which is quite impressive. So how they perform in context future learning. So actually, I have already expanded it just now. They can either do 0 shot or do 1 shot or do few shot by concatenating your input example format 1 by 1, and then teach your model to automatically generate your output. They have shown some good example, shown some nice results on few shot VQA and on few shot OK VQA. So know that the training paradigm is quite different from all the previous methods. As in all the previous methods, you need to do fine tuning, but here is not doing fine tuning, and even not doing prompt tuning or adapter kind of tuning, right? They are just doing in context few shot learning. They also provided some new task format, such as the 2 examples here. In the first one, they show the blanket is a line, while a DAX is a dot, and then you need to learn this pattern so that you can answer the question. And in the second, in the second row, they show another new task called fast VQA. It's basically more than that. Now, suppose you have learned this concept, so I need to ask a question about this so that you can answer it. So the model is great, right? But the language model is only 7 billion. So it cannot have a very strong few shot performance. Then how can we solve this? One idea people have developed is the pica model, because the frozen language model only have 7 billion, but GPT-3 has more than 175 billion, right? So which is pretty much larger scale. However, getting gradients from such a big model could be very non-trivial, which renders training an image encoder to align the language embedding space so very challenging. So in the pica paper, what they do is they want to prompt GPT-3 while the use of image captions. So here they are just simply, so on the bottom right is a task called OK VQA, which focus on a VQA task that requires external knowledge to answer the question. So here, the authors simply treat GPT-3 as a knowledge base, but then translate the images into captions or text so that the GPT-3 can understand it. And by doing this, they show 4 shots can outperform supervised SOTA, and also they have reasonable performance on the standard VQA data set. So what's happening inside? Why GPT-3 are so powerful for OK VQA? The first reason is GPT-3, they encode very rich factual and also common sense knowledge, right? So in the first 2 examples, the question is, when was this type of transportation invented? And if you can, through your image captions, if you can translate the caption to let the model know this is about a yellow train, then the model can roughly guess, can know through the GPT-3 when was this type of transportation was invented. And in the third example, here's more about common sense knowledge. Where can you get this? And then through the image captions generated, we know there's a lot of bananas and other items inside. So the model can know it should be from a grocery store. And the model even can generate answer rationales reasonably well. So it's basically, after doing this, you provide another prompt called this is because, and then let GPT-3 to complete it. And then, for example, in the third example, the rationale will be grocery store is the most common place to get food, which is quite reasonable. So as I just said, converting images into captions could lose important visual information, right? For example, in this image, if your generated caption cannot tell you how many giraffes in this image, usually this is the case, right? Because image captions, standard image captions usually generate generic caption. Then being asked how many giraffes in this, then roughly you can only guess without any further clue. And this is but we still have but the pica also can still have a much better performance than the frozen paper. So now how about if we have enough computing resource and then we can go in beyond this? And I think this is the high level idea behind the Flamingo paper. So the Flamingo paper, if you just see it in a very high level, is still the same image encoder plus text decoder design, if you treat it in a very high level way. But the difference is now the visual encoder and the LLM, which is short for large language model, they are both kept frozen. And also, besides the standard image text files, the pre-training data, they also curated a data set which contain interleaved image text file. They call M3W. And they show this is very crucial for in-context learning capability. And this is how the pre-training data are looking like. So for example, the caption is, welcome to my website, then show a dog image. Then this is a picture of my dog, then it's a cat image. So this interleaved image text file can roughly mimic the downstream task, the in-context learning setting that we need to use in the downstream task. Yeah, as I said before, the visual encoder is pre-trained with clip-like loss beforehand. Yeah, I may need to go slightly faster. So they have multiple modules in this model. The first one is called a perceiver resampler. And basically this is a transformer-like module, which can take as input a variable number of features. So for example, if we want to process video, right? And then it will output a fixed number of visual tokens. They also have the gated cross attention design, which since they have the frozen vision encoder and also the frozen text encoder, how can we bridge the gap? And they bridge the gap through the cross attention design. And they also add the so-called the 10 gates. So that because in the initialization, the 10 gates can be initialized to 0. So in the very beginning of the training dynamics of the LM will not be disrupted too much at the early stage of the training. This is how, so in a high level, when they train their model, they are using autoregressive language modeling loss. Basically, predict the token one by one, while cross attending to the image that preceded in the interleaved sequence. Still, they show good few-shot learning capability, which I will, so very impressive, which I will skip. They also show they can do visual dialogue capability powered by LLM. This is rather interesting because it's not only just SOTA-driven, but they indeed show some interesting things that we cannot do beforehand. But yeah, and this is their high-level results. There are also some other work besides in-context learning if you want to do few-shot. One model is called a field VLM, where they train a small VLT5-like model with prefix LM and MLM. And then they found the prefix LM is very helpful for zero-shot and few-shot captioning, while MLM is more good for zero and few-shot VQA. There's another paper, it's called TAP-C. Well, here is not a GPT-3 model or language model or frozen language model is used. Rather, it's a clip model. And here they show even clip is a few-shot learner for VQA and visual entailment. but then they need to rephrase the task a little bit. So here, given the question, the authors will try to reformulate it as a retrieval task so that the clip can handle. And also for visual entailment, caption and hypothesis, which is text-to-text pair, are used in training, while image and its hypothesis, which is the task format of visual grounding, will be used as the inference. But then the bridge the gap can be closed due to the use of clip, right? Because the clip can map the image embedding into text embedding. Okay, lastly, I'm going to talk briefly about model evaluation. So first, model evaluation is challenging and also it's difficult. So what we do at the current stage is we are going to evaluate on tasks and the data sets like VQA and VL2, visual entailment, VCR, retrieval, captioning, ref coca. They are all good. And indeed, this benchmark have driven tremendous progress in the field, right? So it is non-trivial for a model to grow, to increase from an accuracy like 70 goes to 82, right? Something must happen inside. But then on the other side, they may not be good enough, especially given the fact that big models, they are even surpassing human performance on certain tasks. So here we should try to avoid both overclaiming and underclaiming. When we say overclaiming, it basically means when we use a huge big model and then train this model, fine-tune this model on a data set, which is basically IID distributed, and then you have SOTA performance, but we need to be careful whether they are really have this human-like capability. And in this case, you may need to do a lot of diagnostic tests to say how the model really behaves in the real life, right? But on the other hand, we also need to be careful about underclaiming because there are many people doing adversarial attack, right? And also in the salvation language community, we are also trying to corrupt adversarial examples to hack your system so that your VQA score or your image captioning are totally a mess, right? So here we also need to be careful about this because actually the model has learned something and it's just now you are not, so it's not like an IID setting and also you are not like OOD setting. Basically, you are like an adversarial setting, you want to hack your system. So here we need to be careful. We do not want to underclaim the capability of the models has learned. Also, we should not just focus on topping the leaderboard, but also testing the learned capabilities, which is an open question, I think, for the whole community. It's after we have seen such a tremendous progress on VQA, and also captioning, right? So I think the story is the same, like what have been seeing in ImageNet, right? The performance is already there, and if you still use the original data set, basically you cannot further driven the progress, or the only performance improvement that you can play is something behind. So like a 0.2, 0.5, but how meaningful this is so open question. And indeed, in the field, I think there are some robustness analysis in the field, such as diagnostic tests, challenge sets like OOD, out of distribution generalization, right? Also, the adversarial attack and the probing analysis try to understand the behavior of this kind of data set. And here I'm going to show some example diagnostic tests inside the literature. And at the bottom of the slide is all the references that you can find. So later on, when we put the slides to public. One recently interesting data set is called Flamingo ground. This is a highly curated data set. So basically, you only switch two words inside the caption, but then you want to find such kind of images, right? This is one example in that paper. But then the task is, can you tell which one matches which? For human, this is easy, right? So they are quite different, although the captions they are only slightly changed. But for an AI system, this is very challenging. And even all the SOTA performance behave very poorly on this data set. So we aim to test the compositionality of such models. We also can test the so-called common sense in this kind of models. We can also say how good the model, how good they are at counting, right? We also have data sets, how good the model can deal with question rephrasing, how good the model can do logical reasoning, and how good if we just use some image editing tool to change the image, but then are your answer also going to be changed? These are all open questions. And in terms of OOD generalization, the most famous one is VQACP. I guess if you are in the VL community, you will know it. And another is GQA, right? GQA OOD is also a recent data set. And the recent work, they're also trying to rethink the evaluation practice in VQA with a case study on out-of-distribution generalization. There's also a great benchmark, which is for general robust image task benchmark, which also cover vision language tasks. In this year, ICML, there's another paper, it's called VLUE. And as you can see, one of the key contributions they provide is the OOD test sets. What they say is, although we are doing pre-training, but usually your pre-training data will consider coca images. But then the coca images are also used in your downstream fine-tuning, right? So although you didn't see your downstream annotated data, but the images are being seen. So in this paper by the ByteDance, they provided some OOD test sets. But also VQA. Here we are going to collect the data through a human model in the loop procedure. Well, you have a pair of a model and a human, and then the human will train to generate challenging questions on the fly so that it can fool the model. And so for example, in the image on the right, the first, yeah, so I think I'm on time, but so I'm kind of out of time. I need another 2 minutes to finish the talk, and then we can have the Q&A session. So the first question is, are the kids about the same age? And the model say no, which is good. And then the human will further challenge the system. How many kids are there? And then the model knows, really, right? So which is also right. Then the human will further challenge the model. Is the kid in man's arm youngest? And the model say no, but then the ground truth should be yes. This is a kind of very challenging question. And in the second example is also the same. And the authors find the current sort models, they may not good at this kind of questions, and divided into several categories through some human analysis. So especially, for example, for common sense and for counting and for OCR, and the current model may not good at it. Lastly, briefly talk about probing. There are many papers in probing, and here I just listed 3. And I think, yeah, so it's also a rich literature. So, yeah, let's just skip it. Here, I'm going to provide some high-level takeaway messages in this talk. First, what has been covered? We talk about big foundation model. Compared with big LM, the development of big VL model is still in its infant stage. Second is a few shot in context learning. You will need a big LM at first. Third, we talk about model evaluation, but very briefly due to time constraint. We discuss diagnostic tests, OOD, but also example, and also probing analysis. For future challenges, first, what's beyond simple model scaling? Are larger models always better? Second, beyond the simple text output, can we train a multimodal model that can quickly adapt to tasks that require bounding box output as well in a straightforward manner, which is not covered in the Flamingo work. Third, what do we mean when we say we improve VQA score by another 0.5 points? As multimodal foundation models, they are evolving quickly. I think our benchmark system will also need to be involved. Then the open question is, what's the next generation benchmarking system? With all this being said, I'm going to conclude this talk.